Okay, let's get started here, guys.
What are we doing?
I want to talk about noodles a little bit more. Because I got a little cut short yesterday. This problem has my attention. 29.
There's 40 problems in this thing.
Okay, so here's a sort of kind of boilerplate, kind of classic calculus question. Here's some curve. We might have some idea of what it looks like. If you just think about, like, you know, the end behavior and the behavior near the asymptote, you can at least get a rough idea of what it looks like. But the question is asking, where is it both decreasing and concave up? And so you don't really have to graph it to answer that question, because to be decreasing means that your derivative is negative, and concave up, that means that your second derivative is positive. So like I talked about yesterday with the noodles, there's 4 types of noodles. Okay, so if you think about, if you're just focusing on decreasing, increasing, concave up, concave down, you could talk about how if a function is increasing and concave up, that looks like that. You guys all see how that's increasing and concave up? Mm-hmm. If you were increasing, that's not the letter N. Increasing and concave down, that looks like this. Again, do you see how it's increasing but also concave down? If you are decreasing and concave up, that looks like this. And if you are decreasing and concave down, you look like this. So those are 4 little macaroni noodles. Does that make sense how that is an exhaustive list? Mm-hmm. Meaning that covers every possibility, right? Because there's
2 times 2.
Yeah, very good. It's actually 2 times 2 is 4. So anyway, if I was going to graph this, maybe I'll graph this as an afterthought at the end. But you can just apply that same logic. You can say, what are my intervals where I'm increasing, concave up? Where are my intervals where I'm this? Where are my intervals where I'm this? And where are my intervals where I'm this? And you just piece the macaronis together and make a beautiful macaroni art. You glue them to the paper plate. Sorry, Jesse. Sorry. Okay.
You could just permanently glue them to a real place.
Derivative.
You're at the nerve.
Jesse's just mad at me right now because I had to flex on her earlier with my hashtag sustainable ants on logs containers. So sorry, Jesse.
Well, do you want to see my completely recycled pen that can be composted?
Oh, a compostable pen? Wow. That's amazing.
Wow.
Okay,
Completely
so
recycled. Look at that.
are there any questions on how that's the derivative of that? That's the first derivative, yeah. So that should hopefully be fairly simple by now. Now the question is, when is this going to be either 0 or undefined? If I solve this real quick, let's if you'll allow me, I'm gonna do maybe 2 steps at once. Okay, I'm gonna move him over, right? And then multiply the x squared up. And so you'll end up with this. You'll end up with 3x to the 4th equals 3. Is everyone okay with how I got? I skipped a step or 2, but any questions on? Okay, good. So what's the answer to this? What are the x values? Plus or minus 1. There is one more critical value though, which is 0. It's the asymptote. So on my y prime number line, I've got 3 values on there. Okay. So if I want to know where is this thing increasing, where is it decreasing, I just got to plug in these numbers. So by these numbers, let me be specific, I mean numbers like in this interval. So like 3 or 1/2 or negative 1/2. So, and I'm thinking about plugging them in here. So, and also another clarification. Am I literally plugging the numbers in? Not really. I'm just thinking about if I were to plug in a big number, this would be positive. Okay? If I were to plug in a number very close to, like a positive number close to 0, I'd have a small number minus a big number, which would make it negative. If I plug, same thing if I plugged in a negative small number, I'd have a small number minus a big number. And if I plugged in, say, negative 10 or whatever, I'd have a big number minus a small number. So therefore, my function must go increasing, decreasing, decreasing, increasing. Okay? Is there any questions on that? Good. Okay, second derivative. So I can already narrow down my decreasing interval. It's going to be, I mean, it could be this interval and this interval. It could be maybe one of them, because I don't know the concavities yet. So I got to do the concavity now. So second derivative would be 6x plus, how about that? Are we okay with going from there to there? Okay, good. Same idea, set it equal to 0. Kind of rearrange it. And interestingly, we get kind of a very similar question, right? We get x to the 4th equals -1, is that correct? Okay. So will that ever equal 0? Don't think so, no. So this will never equal 0. So my number line would just have what number on it? Just 0 because of the asymptote. Let's see if that all makes sense. Like if I plug in any positive number, right? If I plug in any positive number, it's positive plus positive. If I plug in any negative number, it's going to be negative plus a negative. Does that all make sense? Maybe, possibly, no, maybe not. Okay, so it turns out then that this whole space here, right, from negative infinity to 0 is concave down, and this whole space here is concave up. Okay. So what's the answer to the question then? What's the interval where I'm both decreasing and also concave up?
0 to 1.
From 0. The answer to the question is kind of a complicated question to get such a simple answer, but there you go. The answer is just from at every x value between 0 and 1. I'm going to quickly demonstrate the whole noodle thing here. So what kind of noodles does this involve? So if I were to graph this, I know you have a bunch of problems where it's asking you to graph it. So what's the first thing I'm going to put on this graph so I don't forget about it? I was thinking the asymptote. There's a vertical asymptote at 0. Right? And so my noodles, now the rest is continuous, right? There's only one asymptote on this function. It's at 0. So my noodles would be increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. So let's put those noodles together. There you go, you're done. Noodly, 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 noodly. You see the noodles? Now, what are these two? I tried my best to draw them. Oh, sorry. What do you think those two x values are? 1 and -1. That's where the Humpty Dumpties would be. The local min, local max. Okay, so does the whole noodle thing make sense, or is it just extra confusing?
It makes a lot of sense.
sense.
This is probably how I initially saw it.
Chicken wing. Chicken wing.
I don't sound that bad, Jesse.
Okay, so
Family's been making fun of my mumbling for the past week, and I'm just about sick of it.
My mom thinks.
So tomorrow's going to be a work day. Monday will be a work day / if you want to look at the practice quiz, you can, and then we'll knock out the quiz on Tuesday. So let's go over. I want to go over a few more questions today.
I hope so.
Let's look at 31. These are always true, false questions. These would be pretty quick. But these, so we're gonna cover 31, some true, false. These are designed to hopefully address any misconceptions. They're kind of tricky questions. And then we're gonna talk about a little bit of just purely graphical questions. Then those should be very quick, actually, just the ones where you're graphing. Okay, true or false? 31A. If f has a local max at 2, then the derivative at 2 is 0. True or false? That would
Oh no, false, because it could be, if it stops there, or if it's pointing.
this one is false. Questions like this bring up I don't know if I'd call it a fault with binary logic, but because is this usually the case? Yeah, usually at a local max, most functions, a local max is caused by,
I'm trying to think where one.
most of the time, a local max happens when the derivative is 0. So this is usually true. But the way true false works, the way that binary logic works is, to be true, it must always be true. Okay, so the counterexample to this would be a local max that's pointing, because in this case, so of course on my graph, it might look like, this is the x value of 2. I could say there's a local max at x equals 2, but f prime of 2 does not exist. Does everyone understand that one, the counterexample?
Yeah. Just because it's a pointy board.
Because it's pointy, yeah. That's pretty much the only there's other counterexamples that are more weird. This is the simplest one. You could have like a piecewise function with like a jump, and you could argue that in this neighborhood, this is the local max and the derivative doesn't exist there. It's discontinuity, but the simplest counterexample for a question like this is just a sharp turn. Does everyone get why that's a counterexample?
Mm-hmm.
Okay. So I know we covered counterexamples last year, but usually I'll quickly review things like if I say true or false. If an animal lives in the ocean, then it's a fish. Fact. That's often true. A lot of those animals in the ocean are in fact fish, but a counterexample would be a dolphin or like a sea cucumber or something. Is that an animal? Isn't a sponge an animal?
That's weird.
Anyway, what's up?
Insects.
I thought insects were a different.
They're in the animal.
Guys, quiet, please.
I don't want to be arguing about this.
Local would be in a small neighborhood of the point. What they do, if in a more rigorous definition, is they say for any, they'll say this. They'll say the neighborhood of 2. They'd say for any, for all tiny epsilons that are positive, there exists some delta such that plus or minus that delta, every point is lower than that. So what I mean is it can be a really small neighborhood. It can be very tiny. So you could have a neighborhood, even if your neighborhood's really small, like a really small little horizontal interval, if I can find a really tiny interval where this is the king, where he's the highest point, then he's a local max. So even if a centimeter to the right, there's points higher, as long as I can find that tiny little interval, then technically it's a local max. Does that make sense?
So with binary logic, how big?
It can be as anything, it can be infinitesimally small, but it can't be 0. So what they say is they say for any, this is not going to make sense. They say for all possible positive values, there exists a delta such that for any x, for any x value, like within that space, so this would be 2 plus the delta, this is 2 minus the delta. Is it theoretically possible to find a an interval,
But how big can it be?
be as big as you want.
Great.
Because like here, I mean, here, well, that's too big.
Yes.
There's a function where the interval is all real numbers. This is the local max. It's also the global max.
Okay, say there were two numbers.
Okay. Okay. This is a local max in this interval, this neighborhood.
But it's not bigger.
Sure. So, but now you're trying to, if you wanted to find the global max, you'd say it's the largest point in all neighborhoods. That's what a global max is.
Okay, say the right points out instead of down.
This?
Yes, it's just.
Okay, this is a local max in this neighborhood. This is a local max in this neighborhood. There is no global max. There's no largest, there's no greatest Y value.
Okay, but if you had that one interval bigger so that it encompassed the other it would no longer be a local max, right?
No, because a local max is if there is a neighborhood in which that is the greatest point on both sides. I mean, you're asking me to get into like this kind of definition, which is well beyond the scope of a Calc 1 class, but is if you can come up with an interval, a symmetrical interval around that point on both sides, where that point is higher than all the points around it, then it's a local max. So if you can come up with such an interval, it's local max. Now that does not say for all possible intervals, because if you say it has to be the highest point in all possible intervals, then now you're talking about a global max. So, does that make sense? It's almost like if you say you're competing, and you're like, well, can I be a chess champion? Is that possible? A local chess champion? Sure, I just got to find a small enough neighborhood where I'm the best chess player, and then I will be the champion. Then we go to like the under 8-year-old division, where they start crying. But yeah, like can you find, so if you take a class called real analysis, you end up playing this sort of game where you say, well, you start off by saying, I'm going to find this interval where this condition is met, and then you go from there. So anyway, we got to move on. So that's a good question though. So hopefully that sort of addresses it, but we can discuss it further if you want later. 31B would be, if the derivative is 0 at 1, then f has a local max or min at 1. False. What's a good counterexample to that? Yeah, like y equals 2. Yeah, that would work. Sure. I like that. That's a very mathematician answer, like a trivial example. Another good one. That's fine. Yeah, that works. I like a cubic function as an example. So this would be something like, this would be x minus 1 cubed plus 1, a shifted cubic. But this function has a 0 derivative at 1. So you can have a horizontal tangent line without having a local max or min. But again, a lot of the time, if you're dealing with a function, here's another cubic, a lot of the time, a 0 derivative does tell you that there's a local max or min, right? But again, true or false? Is this statement ironclad, always true statement? No, not technically, okay? C says, if the derivative is positive between 1 and 4, then f of 2 is less than f of 3.
Just makes my brain
This is a
hurt.
tricky one. So there's a little nuanced thing here. This is true. Yeah, because this says that between 1 and 4, the derivative is always positive. Let me show you an invalid counterexample that students come up with, which is a clever attempt, but it is not correct. They'll do this. Sometimes they'll say, wait a second, no, I can do this. And they'll say that function is always increasing. The derivative is always positive, but clearly f of 2 is not less than f of 3. What's the problem with that counterexample?
That it's not.
Hold on. What, Alyssa? That is the problem. It's the jump. The jump is an issue. It doesn't fit the description. This says that the derivative is greater than 0 for all x values, but the derivative doesn't exist here at some point. So this implies that it's continuous the whole time. So that's not obvious, but that is the case. That if you have a statement like this would imply that the function is continuous everywhere in that interval. And so now let's look at it. Okay, it can wiggle a bit, but it always has to have a positive derivative. So positive derivative means it's increasing. And if it's increasing the whole time, then the y value at 3 must be higher than the y value at 2. Does that make sense?
Yes.
Twin sum always has.
Yeah, because this means it is increasing. It means an f is increasing. You feel okay about that? So this is a big one, big idea in calculus. Positive derivative means the function is increasing. And then the extra leap is, do you understand that f increasing implies that any y value to the right is bigger than some y value to the left in that interval? Okay. 31D. Ooh. This one says. You okay, Hafe?
No,
What's wrong?
I hate big problems.
No, you don't. You love them.
Oh, on contrary. Let's keep going.
So it says if f prime is negative for x values less than 1, and f prime is positive for x values greater than 1, then f must have a local min at 1. So this one, it helps to represent it visually. This says if I drew my f prime number line, then to the left of 1, I have a negative derivative, so I'm decreasing. And to the right of 1, I have a positive derivative, so I'm increasing. Does everyone understand that? How I translated the sentence into a picture? No? Okay. Now, here's the question. Does that usually tell us that, like, let's say we knew the function was continuous? Oh, yeah, there would be a local min there. But there's a simple counterexample to this. Decreasing, increasing. Does this function go negative derivatives to the left of 1, positive derivatives to the right of 1, but there's no local min? So this is my counterexample. You okay with that?
Yeah.
E, very similar question. It's actually identical. There's just one extra caveat. What's the extra caveat here?
Continuous.
It says it's continuous, so I can't have an asymptote. So now I'm kind of forced to go negative derivatives. Even if it's pointy, it still's fine. If I go negative derivatives and then switch to positive derivatives. So whether I have it pointy there, then no matter what, you're always going to have a local min at 1. So E is true. Okay with that? Say it again.
But I think that there are points like maximum.
No, so this this pointy, it is a local min.
I think that points couldn't.
So back on question A, what we said was, this is one of those, this is one of those like all, what is it? All, blanking on a simple example of this, where you go, all hippos are mammals, but not all mammals are hippos. So you can say, does hippo imply mammal? True. Does mammal imply hippo? No. So here, now that's a simple example, obviously, but so something like this, when we say, does a zero derivative, like sorry, if I say, does a local max imply, or local max or a min, does that imply a zero derivative? No. I guess this one doesn't work either way because a zero derivative doesn't imply local max or local min. But on question A, what we're saying is, it doesn't mean, sorry, I'm getting stumbled over my words here, but appointee is a counterexample to A, question A, but not for question E, because question A is saying if local max, then zero derivative. This is a counterexample because it is a local max. This is true, but the derivative is not zero, it doesn't exist. Whereas on E, it's just saying that what if the derivative is positive to the left of 1, and then the derivative is, sorry, the derivative is negative to the left of 1, and then the derivative is positive to the right of 1. Note the big thing on E is it never brings up this. This is never mentioned, right? So even though the derivative doesn't exist at 1, you can still have a local in there. So just hopefully what I'm saying makes sense. Huh? No, it doesn't.
No.
Okay, how about F? This says if the second derivative is positive, in your mind you can translate that. When it says F double prime is positive, concave up. So it's saying if you have a concave up function, it's concave up between 1 and 8 at least. Does F of 4 have to be bigger than F of 3?
No.
The answer to that is no. That is not necessarily true. What's a really simple concave up function? A function that's concave up everywhere, a parabola. So it's not hard to just draw a parabola. The nice thing about a parabola is I don't even have to worry about it. I'm guaranteed to be concave up in this interval if I draw a parabola. So can I draw one where F of 3 is not less than F of 4? I mean, if I just draw a simple parabola like this, I'm good to go because this thing has a positive second derivative everywhere between 1 and 8. It's concave up. But F of 3, here's F of 3. Oh, did I do it backwards? Yeah, sorry, I'm dumb. My bad. I misread it. I thought it said F of 3 greater than F of 4. Sorry. Just draw it differently. My bad.
No.
Well, now,
Just testing this.
just testing you. There you go. So now it's still concave up. And here's my F of 3. Here's my F of 4. And as you can see, it is not the case that F of 3 is less than F of 4. So all I had to do was draw, basically, it's all macaroni. It's all macaronis, guys. I just had to draw a macaroni that was decreasing while being concave up. What's wrong, Cooper? You okay back there, Brett? Huh? Never okay? I know. It sucks. Life is pain. Okay. G says if f prime of 2 is 0 and it's concave up, is there a local min at 2? That is true. This one you can really get in your own head the harder you think about this. And like what you were talking about, Rafe, if you start really zooming in on something and talking about like how tiny can this interval get where it's still valid, this question can be kind of confusing. But if you look at a very simple example, if you kind of underthink it, it just says, like, what if I had a curve like this where it's concave up? So there's my f double prime of 2 being positive, and f prime of 2 is 0, meaning a horizontal tangent line. Is that a local min? Yes, so this one.
I
Yes.
have a question on that one. So because it's concave up, so it's positive double derivative, but it's like flat. So is that just because it's transitioning from concave down to concave up? Like that's the transition point?
No, this whole thing is concave up.
Oh,
That's all concave up. Well, sometimes people will go, wait a second, what if you were just talking earlier about a function like this where the derivative is 0, but there's no local min there, right? But here's the problem. At that point, it's not concave up. it's changing from concave down to concave up.
That's
So then you go, okay, fine, I'll just put a little bit of a wiggle in there. So now it's concave up there, but now it's local min. Ever so slightly, it's a local min. Because in this little tiny neighborhood, that's me entering the under 8 chess tournament and crushing the children and becoming the local champion. Right? This is a local min, not a local max. But same idea. Anyway.
And failing completely, entering the, under 8 chess tournament and just, completely failing, getting demolished.
I think I could win in an under 8 tournament. I think I could.
I think you could win at a tournament. You're pretty
No,
good at
not
chess.
if they were like 12, I'd get crushed. I'm serious.
Honestly, younger kids are so much
A
better.
12-year-old who like plays competitively with a coach would destroy
Well,
me.
yeah,
with that
that
knowledge.
makes sense, yeah. I just said just random people.
Oh, sure. Random 12-year-olds, yeah, I could beat them.
Random, yeah.
They're probably not going to be at a chess tournament, though. Anyway, let's move on. Okay. 31H says, it's just it's sort of the reverse of that. If your derivative is 0 and your concave down, is there a local max? Yes. H is true. Okay.
Yeah.
So G and H, I don't know. Those are two that, if you think hard about those, it probably will help your understanding of this stuff in general. If you really understand why those are true. Okay, and then I is a weird one, but it's going. Here's a way you can. What's up?
Mr. Peacock told us to come ask you for a vacuum pump.
So be careful. It leaks oil, so don't get it on your clothes. It's in that to the left. It's in the bottom. Nope, you got it. That cabinet to the left. No, that thing to the left. Right there. And it's the bottom drawer. Okay. Be careful. I think I told Mr. Peacock it leaks, so just he'll be careful. So, anyway, so yeah, no problem. I says. So here, what I was saying, sorry, is you can check your understanding here. Can you read this sentence? But don't read it literally verbatim. Don't read it if f double prime of x is greater than 0. Don't read it that way. Read it if the function is concave up on the left side of 0, and the function is concave down on the right side of 0, and the second derivative at 0 is 0. Then there's a local max at 0. So try to visualize that in your head. If your function goes from concave up to concave down at 0, does that imply a local max?
No.
No, definitely not. Here's a really simple example. This function is concave up and then concave down. So a simple like y equals negative x cubed function. This certainly goes concave up, changes to concave down at 0. It also has 0 concavity at 0, but certainly no local max. So this one, in fact, I think is very false because it might not even be possible to construct a function that does that. Maybe it is. I don't know. I'm sure it's possible. Well, no, not anything.
Well, okay. So you were just saying about like the infinitesimally small thing, right?
Uh-huh.
Is there another number besides 0 that would equal 0 on that function? So then why wouldn't it? Oh no, never mind. Hang on. Wow. More entirely. No.
Yeah, it's kind of like saying, like, take a function like 1, or it's almost like saying, think of the smallest number you can come up with. Okay, I'm imagining the smallest number, and I just go, okay, cut it in half. That's part of the game of like, when you do a very rigorous definition of like, say, continuity, or the definition of, even the definition of differentiability and stuff. The big one's continuities. We take this analysis class. We should only take that if you're a math major, pretty much. Other STEM majors typically don't take that. But yeah, you get into these very rigorous definitions, which are effectively a game where you say, I'm thinking of the smallest number I can think of. Oh, Mr. Thompson.
Mr. Hall, have you seen the vacuum pump?
It's just taken by 2 students. They bring it to Mr.
did they?
Peacock.
Okay. So you had it?
Yeah.
Okay, great. Thank you.
Okay, I think I'll save, hopefully those questions made sense and they can inform your work on 32 through 35. 36, we've already done. Think about that. Have we already, what, you're like, what? We did 36? When do we do 36?
We did 36.
It's the noodles, yeah. We did it earlier. So if a function is, so 36 says, is there a function that's increasing and concave up for all x? Maybe we didn't cover the for all x thing because you're like, wait a second, noodles are not infinitely long, are they? I wish. So if you want to be, so for like 36a, who can tell me a famous function that's increasing and concave up? X squared doesn't quite work because it's not increasing for all x.
It's like the
X cubed?
Close?
Natural.
Close?
Whatever.
A function like, yeah. We don't know how to take this. We haven't studied this in a calculus context yet. Well, we're studying it conceptually right now, I guess. But we know this just because it's like a fact we know that the exponential growth looks like that. But you can just see visually that this is a function that is concave up everywhere and also increasing everywhere. So the answers to all four of these questions are going to be either like an exponential growth, an exponential decay, or maybe a negative exponential growth, that kind of thing. That's all you get to do. Fun fact of the day, what's the derivative of e to the x? E to the x. It's a famous function. It's a famous function that's equal to its own derivative. In fact, that's kind of what makes e famous to begin with. We didn't know that before. We went, oh, well, e is this number that pops up when you study exponential growth. But if you really think about it, it's actually, that's precisely what exponential growth is. It's when the growth rate is proportional to the size of the thing. Thus, anyway, we'll get into that later. What's up, Raven?
Why wouldn't it be x e to the x minus 1?
Because that rule only works if it's x to a number power. If x is the base, then that power rule holds. And you can derive this using the limit definition of the derivative. Okay. All calculus questions of why does that function have this derivative? Every single time the answer is, well, if you look at the definition of the derivative and do a whole bunch of crazy algebra, you get this result. So this can be derived from the limit definition of the derivative. But if you're dealing with this, it won't pop out that way. It just turns out that it's equal to its own derivative. Okay, 37 and 38. What kind of method could you use on a question like that? Huh? Noodles. Just make noodles. Just make noodles. You can do those. It doesn't specify in that question if those numbers are like, those could be points where the derivative is undefined, or they could be points where the derivative is 0. You're not really sure. So there's a many different answers to these questions. So like on 37, for example, let's do 37 together. I don't know, can't hurt, right? 37. So how many different noodles are there on 37? There are 4 noodles. So if you look at 37, now if you're getting confused at all, I'd recommend just drawing a second number line and combining the first two and saying, okay, that in this interval we are increasing while also being concave up, right? On this interval we are decreasing while being concave up. I guess they're all concave up, aren't they?
Yeah.
So it goes increasing, decreasing, increasing, decreasing. But it's also concave up the whole time. So how does that work? How are we always concave up? Well, it's noodle time. So one way to do this might be, here's -2, here's +2, here's 0. Someone said pointies, right? So it could be,
Look over.
does this work or does this need to be fixed? Increasing, decreasing, increasing, decreasing. Yeah, that looks pretty good to me. Could these be asymptotes? Could they go? Yeah, sure, they can be asymptotes. The number line does suggest, be careful, on 37, you don't want an asymptote at 0 because the number line suggests that the second derivative exists at 0. So there's a pretty clear implication that the derivative is 0 at 0. Anyway. Okay. I think that I could be wrong, but I think 39 and 42 will be straightforward based on what we've talked about. It's just like a lot of noodly woodlies. So the last thing I want to talk about today, and we can talk more tomorrow, but I wanted tomorrow mostly to be a work day, is I want to look at these purely graphical ones, like 46. So the last few questions on this problem set, you'll notice that they're all like this. So I know that, like, 46 through 59 or whatever, 58, that's 13 or, no, sorry. Yeah, 13 questions. But they're just graphs. They're actually pretty quick questions. So 46 says, how do you go from this graph? Let's say this was your f. What does the graph of f prime look like? Now notice, you're not given a function, so you can't use like a product rule or a quotient rule, or there's no calculations, purely visual. So what do you do? Now they didn't like come out great on the printer, but there should be little notch marks here that you can kind of see like where it changes from, increasing to decreasing and stuff. So look what this graph says. This says that my f prime, what is f prime doing over here? It's positive. F prime is positive. It's also increasing because it's concave up here. But the most basic level of this is just f prime is positive, then it's negative, and then it's positive. So this function over here has to be positive, then negative, and then positive. Does that make sense? Positive, negative, positive. Yes, no, maybe so. And then also, what should my derivative be approaching on like the far ends, for example? Yeah, those are pretty flat. It's a pretty flat function, right? So 0 derivative, but it's positive. So I've kind of already got the end behavior. Did that end behavior idea make sense or no? So it seems like, and then we're gonna have a max, so a min, so it's a negative derivative there, right? And then the derivative is equal to 0 at -1 and 1. Is this all making sense, or is this?
Yeah.
There's not exactly a step-by-step procedure that you need to follow on these. A lot of it's just kind of like just reasoning it out. It's kind of abstract. So anyway, my function then has to go
2 points there.
Yeah.
okay.
That's fine.
So notice my derivative it was positive numbers, negative numbers, positive numbers. And then also, I know Bell just wrong, but if you look at the concavities here, concave up, concave down, concave up, concave down, translates to this function going increasing, decreasing, increasing, decreasing. So we can talk more about those, a few more tomorrow, go over some more examples. But.